delta G equals delta H minus T delta S. And this is called Gibbs free energy. It takes input from both enthalpy, which you guys mentioned, and enthalpy as well as entropy. And what else determines whether a reaction will move forward or not, or stay in the reactant side? What else plays a role? What else? Okay, T. What's T here? Temperature, very good. So sometimes reactions, if you increase the temperature, you can make the reaction go to products. Sometimes you can lower the temperature and then you can make the reaction go to products. Okay, so all these things come together. This delta G, which stands for Gibbs free energy, okay, it takes input from enthalpy and entropy. All right, my final question here is a review. If your delta G is negative, what does that mean the reaction becomes? Does it favor products or reactants? Products. It will definitely favor products. And what type of reaction is this? Yes, exergonic. Very good. Anybody here take a biochem or biological chem or any of those type of classes? Bio maybe? They talk about delta G in some of your textbooks. So if your delta G in a cell biology class or whatnot, if your delta G is negative, that reaction is going to release free energy and favor products. If this Gibbs free energy is positive, okay, what does that mean? What type of reaction is this? Okay, the opposite of exergonic. What's the opposite of exergonic? Okay, endergonic. And what will this reaction favor? Will it favor the products or the reactants? Okay, it's going to favor the reactants. And if you plug in your delta H, your T, and your delta S to this equation, and it turns out to be positive, that's an endergonic reaction. It favors the reactants, does not favor the products. And does it release free energy, or does it require free energy? Okay, the opposite of your negative, it requires free energy to make the reaction favor products. Requires free energy. So this is kind of a sort of review of what we've talked about so far in Chapter 17. Okay. All right, let me very, very quickly go over this. Okay, relationship with the N. Let me zoom in here. Relationship between the entropy of the surroundings. Now, what is the surroundings? Okay, surroundings is like everything else, right? It's like the universe. Okay, the surroundings also include the beaker. So when you do your lab today, the surroundings is the styrofoam cup. The surroundings is that calorimeter, that gray thing. Okay, you'll see it when you go there. Okay, those are the surroundings. Okay, and what is S or delta S? Okay, that's entropy, disorder. Okay, what is delta H? Enthalpy. Okay, what is the system? Reaction. The reaction is the system. Okay, in this case for this lab, it's the NaNO3, the sodium nitrate. That is the reaction, okay, and the water. okay, water and NaO3. So those are the chemicals, okay, that will do the reaction. The surroundings is everything outside of it, everything, okay, the cup, the calorimeter, you know, the room, you know, essentially it's the universe, okay. So we're comparing the entropy, the disorder of the universe, delta S, versus the enthalpy of the system, your actual reaction that's going to take place. Okay, so this is the relationship between those two. Okay. So if we have a situation where your enthalpy is negative, okay, remember enthalpy is delta H. If your enthalpy is delta A, if your enthalpy is negative, your delta H is negative. Okay, that is an exothermic reaction. Okay, but what will the entropy of the surroundings be? Ordered or disordered? Okay, negative into negative is positive. So what would your delta S of the surroundings be? The universe, the entropy of the universe? Okay, more disorder. Right. So if you're having an exothermic reaction, it releases heat. It releases heat to where? The surroundings. What happens to the surroundings? Do they become more ordered or more disordered? Think about it. Will they become more ordered or more disordered? They should become more disordered, and that's what this relationship is saying. Okay. If you blow air into the universe, okay, does the universe become more ordered or disordered? Okay, it'll become more disordered. It's not like all the air molecules are going to go orient themselves to go that way in that corner of the room. Okay, that is a phenomenon that requires order. Okay, disorder means randomness. So an exothermic reaction will cause more disorder to its surroundings by releasing heat to the surroundings. Surroundings take that heat, and that causes more disorder to it. Okay, so that's the relationship between this. In some cases, if you increase the temperature, okay, if you increase the temperature, what you're doing is you're causing more disorder to the system. Look at the temperature, it's in the denominator. If you increase the temperature, you're causing more disorder to the system, but you're causing more order to the surroundings, okay, because this value goes down. The opposite situation, if your enthalpy delta H is positive, okay, just doing this equation here. This is an endothermic reaction. Okay, and if this is endothermic, your delta H is positive. Positive into negative is negative. Your delta S of the surroundings is negative. Okay, which means you're getting into a situation where you're having more order. So this is coming from this equation right here. Entropy of the surroundings, enthalpy of the system. Entropy of the surroundings, enthalpy of the system. All right, let's go now really quickly, talk about the third law of thermodynamics. All right, so the entropy of a pure crystalline substance is 0 at absolute 0 temperature. The entropy of a pure crystalline substance is 0 at an absolute 0 temperature. Okay, absolute 0 is where K is equal to 0. Okay, Kelvin. And the entropy of that is 0, meaning essentially there is no molecular motion. Okay, no molecular motion, no vibration motion, no rotational motion, no translational motion. Okay? So this is very hard to achieve. Okay, a pure crystal should have a pure, okay, the key word here is pure, 0 molecular motion, 0 degrees of freedom, okay, its entropy is 0, okay. So that is a situation where the third law of thermodynamics, that entropy is 0 for a pure substance at absolute 0 temperature. Okay. And at absolute 0 temperature, you would have no molecular motion. Yeah, that's like perfect order. Okay. So do you guys know anything about crystals or diamonds or things of that sort? Okay, diamonds. One of the reasons diamonds are so valuable is it's a crystal. Okay, and crystals are composed of unit cells. Okay, just like unit cells that we saw in that lab many weeks ago. So unit cell you can think of as a brick in a brick house. Okay, and they're packed like this. Okay, the atoms are packed in lattices like this. You can actually do X-ray diffraction studies and determine, the arrangement of the atoms. They crystallize DNA. You can make DNA crystals. You bombard it with X-rays. The X-rays will diffract those atoms. And from that diffraction pattern, you're able to, backtrack to calculate the structure of the DNA or the protein molecule or what have you. Okay, so our crystal, if it's very, very pure, and this is why it's very expensive, all of those unit cells, all of those atoms in those lattices are very, very rigid, and there's no motion. Okay, why is there no motion? Because in the third law, your Kelvin is 0, okay? Absolute 0 temperature. So this is a situation where absolutely nothing happens, okay? Because, molecules are always in motion. And the bonds are also motioning. Also, the bonds are vibrating. You can actually measure bond vibrations using IR, infrared spectroscopy, which is bond vibrations. That doesn't happen at absolute 0, okay? For a pure crystal, this also will have like 0 entropy. So it's the most ordered substance there is. Most ordered substance on the planet. Okay, the more pure it is, the more ordered it is. The real thing is that you really can't get to this state. You can get to absolute 0, but can you get a pure crystal? Okay, the answer is no. This is why they're so expensive, and this is why the diamonds are so expensive, because the unit cells should be ordered and they should line up and stack with one another, but every now and then you'll have a unit cell that's off. Okay, if you do look at it under a microscope or do some X-ray diffraction, you'll get a unit cell that's 1 degree off or even 0.5 degrees off from its organization. Okay, and that is a disorder. Okay, so this is called twinning. This is not something I'm going to test you on, but twinning means, and crystals have this problem of twinning where the unit cells are a little bit off juxtapositioning. So they're off by 1 degree or even less than a degree. And that messes up the organization, that messes up the purity, and that messes up the entropy, even if you're at absolute 0. So this is why crystals are very, very in high demand, are very, very expensive. Okay? Because it's hard to get this perfect alignment of those unit cells. Okay? But if you were to get perfect alignment of the unit cell, like in a crystal or any type of crystal or like a diamond, and if you were to put it at Kelvin equals 0, absolute 0, then you'd have no motion. And then you'd have no entropy. Okay? So that's what this third law of thermodynamics is stating. Right? So there's three laws: the first law, second law, and this is the third law. All right. All right. I just thought you'd like to know, but I'm not going to test you on twinning and crystals and disorder and all this stuff, order, unit cells. I'm not going to tell you that. All you need to know is just basically this definition, and that's perfectly fine. Okay. But, finding a pure crystal is really hard, and that's why they're so expensive. They're found in mines or caves or wherever. All right, now let's go to Gibbs free energy. All right, this is the final okay, the final factor that determines whether a reaction will proceed to products or not. And then, as you guys mentioned, okay, if it's negative, it's an exergonic reaction. If it's positive, it's an endergonic reaction. All right, same as equation that we did on Monday before we took the exam. Okay, we'll take sum of the products of the standard free energy of formation of the products minus the sum of the standard free energy formation of the reactants. Okay, standard state. Okay, that little not symbol means standard state. So delta G decides it all once and for all. I think we mentioned this already. I'll go over it one final time. This is what you need to know for this chapter and also chapter 18 when we talk about electrochemistry. Okay, when you do, you put it into the equation and it's negative. This is an exergonic reaction, and this is a reaction that favors products. Okay, I just wrote this in the previous page, but I'll write it again. Okay, the equilibrium, if it were an equilibrium reaction, would favor the products. Okay, this is called an exergonic reaction. All right, if your delta G is positive, okay, we're favoring the reactants. Okay, it does not move forward to products. It's called an endergonic reaction. And it requires energy. Okay, if your delta G is 0, it does not favor reactants, it does not favor products. Okay. All right, let's look at this together here. All right, so we have delta G, which is the final judge and whether the reaction is going to go to products or not. Gibbs free energy, delta H minus T delta S. Okay, or you can have it at standard state, which is right below it. All right, let's say your delta H is negative. Okay, your delta H is negative. If your delta H is negative, what type of reaction is that? It's an exothermic reaction, so it's going to release heat. It's going to release energy. Okay, if your delta S is positive, is that spontaneous or non-spontaneous? Spontaneous, okay, that's an increase of entropy. So if you have a reaction that releases heat, and we already determined that if it releases heat, the surroundings get more disordered. So if you have a reaction that releases heat, if you have a reaction that is spontaneous or, leads to more disorder, then regardless of the temperature, your delta G will always be negative. And if your delta G is always negative, that's an exergonic reaction, and this will be a reaction that will favor the products no matter what temperature. Okay, so this reaction is, okay, if your delta H is negative, okay, I'm going to call it an enthalpically favored. Enthalpically for enthalpy. Enthalpically favored. And if the delta S is positive, that's entropically favored as well. So regardless of the temperature, this is the best situation. This is a reaction that you don't have low temperature, high temperature, any temperature. It's enthalpically favored and entropically favored, so it's going to be exergonic. The reaction is favored to go to products. So in terms of enthalpy, it's enthalpically favored. In terms of entropy, it's entropically favored. Okay, this is all coming from this equation. Okay, what happens if your enthalpy is positive? Okay, this is called an endothermic reaction. So this is a reaction that's not favored to go to products. You need to provide energy to do that. So if it's positive, that's endothermic. Okay. If the delta S is negative, that means it is non-spontaneous, or in other words, leads to more order. So those are situations that don't just happen by themselves. Okay, so this reaction needs heat to go. That's endothermic. This reaction tends to move towards more order, which means that you have to provide some work to get it from disorder to order. So in this situation, no matter what temperature you put it in, this will be enthalpically disfavored and entropically disfavored. If you put a positive in here and you put a negative in here, regardless of the temperature, this will always be positive. Okay, will always be positive, the delta G, the final judge. So if you put a positive in here and a negative in here for your S, your delta G will always be positive. So it's disfavored enthalpically, and it's disfavored entropically. So I'm going to write here enthalpically disfavored. Okay, plus entropically disfavored. All right, what happens if your delta H is positive? Okay, that's an endothermic reaction. It requires heat. What happens if your entropy is positive? What does that mean? It leads to more disorder. So this is a reaction that's enthalpically not favored because it's endothermic, but it's entropically favored because it's positive. Remember, if it's positive, it's going towards more disorder. So what do you do to make that reaction go to products? Okay, you're going to raise the temperature. Okay, it's only at high temperatures will you get the delta G negative. Okay, so you raise the temperature if a reaction is endothermic, but it's spontaneous. Okay, so this is enthalpically disfavored. Okay, but it's entropically favored. Entropically favored. Okay, how do you make that reaction go to product? Because it's favored in terms of entropy, but it's disfavored in terms of enthalpy. I'm sorry. It's disfavored in terms of enthalpy, favored in terms of entropy. How do you make the reaction go to products? You raise the temperature T. You raise the temperature T, there's more disorder. You force this to become more negative, making the delta G more negative, which is what you want if you want the reaction to go to products. All right, finally, if they're both negative, okay, negative, that is an exothermic reaction for delta H. But if your delta S is negative, that just means it's moving towards order. Okay, not disorder, but order. So this is a reaction that's enthalpically favored, but entropically disfavored. Okay, how do you make a reaction move to products that is enthalpically favored? That's the null minus sign, exothermic. But it's disfavored in terms of enthalpy because the delta S is minus, moving towards order. Okay, so this is entropically disfavored. Okay, so how do you make that reaction go to products then? Okay, here you will lower the temperature. Okay, when you lower this temperature, the minus sign of the delta H gets more amplified, making the minus sign of the delta G more amplified. You lower the temperature, make the delta H more negative. Okay, so lower the temperature to make the reaction go to products. Okay, so this is what you have to do. So some reactions you lower the T. Actually, it's those reactions that are enthalpically favored and entropically disfavored. You lower the temperature to get to products. In a reaction that's enthalpically disfavored but entropically favored, you're going to raise the temperature. Okay, so this is all thermodynamics. Okay, this is like really hardcore thermodynamics. All right, so energetics. All right, so ultimately, if you want to go to products, you want your delta G to be negative. Okay, exergonic. All right, here is an equation that I'll give you for this upcoming exam. Delta G is equal to delta G at standard state plus RT natural log of Q. Okay, and then R is our gas constant, 8.314 joules over mole Kelvin. And you know what this delta G is, right? This is the delta G. Okay, we know what this delta G is, right? This is the delta G at standard state. Okay, and this is the delta G at non-standard state. Our TT is temperature natural log of Q. Okay, do we remember what Q is? Okay, Q is called the reaction quotient, and we use Q to compare to K. All right, Q. So if you have an equilibrium reaction, this equilibrium reaction has an equilibrium constant K. That's products over reactants. Okay, but we will not put solids or liquids in that products over reactants. And then what we do is we use this Q and compare it to the equilibrium constant K. Okay, comparing Q to K, we can use the Gator rule, okay, in this equation. All right, let's put Q first. Okay, if Q is greater than K, where do the alligator jaws go? Okay, the alligator jaws point to the reactant side. All right, so that means the reaction is going to shift to the reactants. If a reaction favors the reactant side, if the reaction favors the reactant side, what do you think the delta G would be? Positive or negative? Exergonic or endergonic? Okay, what is the sign for an endergonic reaction? Reaction that doesn't go to product, stays in the reactant side? Positive. If your Q is less than the equilibrium constant for this reaction, okay, where do the alligator jaws point? To the product side. Okay. Okay. Now, where do the alligator jaws point? To the product side. So which way will the reaction go? To the product side. What do you think the free energy for this would be, positive or negative, if a reaction favors the products? What would it be? Negative, yep. Okay, this would be a exergonic reaction. Okay, very good. And then finally, if Q is equal to K, it's going to shift neither. And it shifts neither. Your delta G is neither positive, it's neither negative, it's just zero. Okay, and this is an equilibrium. Okay, where your delta G is equal to zero. Okay. It's not favoring the reactant side, it's not favoring the product side. Okay, so all of this goes to this equation right here. Okay, R we know, that's given, and then T is the temperature. How will we get to delta G? Okay, we use this equation using the free energy formation from the textbook. Okay, so this is the equation. Okay, I'll give you that on the exam. Okay, let's say we are at equilibrium. So if Q is equal to K, then this delta G is equal to 0. Okay, because it's not positive endergonic, it's not negative exergonic. If Q is equal to K, delta G is 0, so I'll put in a 0 here. Okay, Q is equal to K, and then we'll get our another equation here where delta G at standard state is minus RT natural log of K. Okay, this is another equation that I'll give you on the exam, and that's on the next page here of our notes. Okay, so two equations with the delta G, the free energy. Actually, three equations, and I'll give you those on the test. Okay, so here we're dealing with K, not Q, K. Q tells us where it will shift. K is the actual equilibrium for the actual equilibrium reaction. Reactions at equilibrium. Okay. All right, if K is greater than 1, we know the products are favored. Okay, very large K favors the products, remember? Okay, if you have $1 million, you're moving forward. A very small K means the reactants are favored. Okay, and if your K is equal to 1, products over reactants is equal to 1. Neither products nor reactants are favored at the end of the equilibrium. All right, so that is one equation here, and then this is the other equation that tells us which way the reaction will shift to get to equilibrium. And this equation here will tell us if the reaction is enthalpically or entropically favored. Okay, and whether we got to raise the temperature or lower the temperature to get our products. All right, the last two problems on this chapter, and then we're at good pace to start our last chapter and also have some reviews to go over this material again. Okay. All right, let's finish off these two problems, and then we'll take a break and let's head off for lab. All right, calculate the equilibrium constant Kp for the reaction 2O3 goes to 3O2. Okay. And the equation for the equilibrium constant is going to be given on the exam. Kp, right? And then how are we going to get to delta G of the reaction at standard state? Okay, sum of the products minus sum of the reactants. All right, what is our product here? O2, what is its free energy of formation for O2? Oh, it's 0. Okay, that's fine. We can always look it up in the back of our textbook or online. It's 0. That's for 1 mole. But how many moles do we have? 3. So we're going to take that 3, multiply it by 0. Okay. Minus, I want you to put a big bracket here for the reactants. Minus the sum of the products minus some of the reactants. So what is the reactant here? O3 gas. And what is its standard free energy of formation? 163.6. That's for 1 mole, but how many moles do we have? 2. So we're going to multiply that by 2. Delta G for this reaction at standard state. What's 2 times 163.6? Oh, I don't have my calculator. Minus 327.2. Is that what you guys got? Okay, so that's the delta G of the reaction. Say it again, I'm sorry, Michael. Sum of the products minus sum of the reactants. Negative, yeah, negative. Yes, negative. And then let's plug that in here. So it's going to be minus 327.2 kilojoules per mole equals minus. Okay, I have a problem here. Okay, I want everyone to pay attention. R is, what is R? Okay, I'll give you R as a constant. It's 8.314 joules over mole Kelvin. Okay, that's not the problem. Okay, the problem is that, what do I have it here now? Kilojoules per mole. That's right, very good. So I'm going to convert this to joules per mole. How will I convert that to joules per mole? I got to multiply it by 1,000. Okay, 1,000. So minus 327.2 kilojoules per mole times 1 kilojoule is 1,000 joules. Okay, now I can plug it in here and solve for Kp. Minus R minus 8.314 joules over a mole Kelvin minus RT. What is T here? 290. Thank you, Allison. Good. I got my cheat book, so, or not cheat book. and then natural log of Kp. All right, so natural log of Kp is, but I want you to use the calculator, make sure I did it right, is minus 327, 200 joules over mole divided by 8.314 joules over mole Kelvin, and then 298 also gets divided in there. Okay, this equals to the natural log of Kp. So the Kelvin cancel, joules, mole cancel. And then, what's this number here? I may need your calculator. So minus 327,200 divided by, so the minus cancels, divided by 8.314 times 298. Thank you. Awesome. Do you guys know how to do this on your calculator? That's why I took Allison's calculator. Just make sure you know how to do it. That's all I'm asking. Okay, the minus cancels. So it's going to be 327,200 divided by 8.314 times 298. Close those parentheses. 132.064. Let me just write that down. 0.65 equals natural log of Kp. All of this, I did it on my calculator, or on Allison's calculator. I got this is equal to 132.065. Okay, how will I get to Kp? Okay, we do the inverse natural log, which is e. E to the power of 132.065 equals Kp. And what is that on our calculator?
The this 2 down from the second button.
Shift.
Oh no.
No, not.
You don't have to press the second button, but it's better.
Perfect. Got it. Awesome. 132.065. 2.27 times 10 to the 50. Yeah, okay, this is a huge number. 2.27 times 10 to the 57. This is a reaction that overwhelmingly favors the product side. That's huge. Excuse me. And that would be the answer. Okay. So this favors the product side. I got something in my throat. What does the minus sign tell you? It too favors the product side. So exergonic, okay, minus delta G. Huge Kp favors the product side. The equilibrium and the delta G free energy corroborate one another.